Hello, and welcome to this seventh set of problems on complex numbers. In this set, we will solve problem number 61 to 70. So, as I always say in the beginning of my videos, that you should pause the video when I'm stating the problem and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. So, without further ado, let's get started. Problem 61 says that if Zn is equal to cos pi by 2n plus 1 into 2n plus 3 plus I sine pi by 2n plus 1 into 2n plus 3, then find Z1 product of Z1, Z2, Z3 up to infinity. So in this case, the angle of cos theta, cos and sine can be written as 1 by 2n plus 1 minus 1 by 2n plus 3 into pi by 2. So here also we have written that. Once we have that, we start substituting value of n as 1, 2, 3. So we will get 1 by 3 minus 1 by 5 for n is equal to 1. 1 by 5 minus 1 by 7 for n is equal to 2. 1 by 7 minus 1 by 9 for n is equal to 3, and so on for sine. Now if you see, 1 by 5 will get cancelled. 1 by 7 will get cancelled, 1 by 9 will get cancelled, and so on. So what we will be left with is 1 by 3. And when you multiply that with pi by 2, it becomes pi by 6. So the final answer is cos pi by 6 plus I sine pi by 6. Problem 62 says that if Z1 and Z2 be two complex numbers and A and B are two real numbers, then prove that A Z1 minus B Z2 mod whole square plus mod of B Z1 plus A Z2 whole square is equal to A square plus B square into mod of Z1 square plus mod of Z2 square. To solve this problem, we take Z1 is equal to x1 plus iy1 and Z2 is equal to x2 plus iy2. So when you substitute the values and square it, you will get ax1 minus bx2 whole square plus ay1 minus by2 whole square plus bx1 plus ax2 whole square plus by1 plus ay2 whole square. Now it will have this expansion, and you will see that 2ab x1 x2 will get cancelled over here and over here. 2ab y1 y2 will also get cancelled. So from these two. So from rest you can take a square plus b square common, and the term which will be the product of this is x1 square plus y1 square plus x2 square plus y2 square. Now x1 plus y1 squared will be z1 square, mod of z1 square, and x2 square plus y2 square will be mod of z2 square. So that gives us our desired result. Problem 63 says that show that the equation a square by x minus a plus b square by x minus b up to h square by x minus h is equal to x plus l, where a b up to h, capital A b up to capital H, and small a to small h and L are real, cannot have imaginary roots. So we let x is equal to y plus iz. So the given equation becomes a square by y plus iz minus a plus b square by y plus iz minus b up to h square by y plus iz minus h is equal to y plus iz plus l. Now we rationalize this by multiplying each term on left hand side with complex conjugate and dividing with complex conjugate. So the equation will become a square into y minus a minus iz by y minus a whole square plus z square plus b into y minus b minus iz by y minus b whole square plus z square, and so on. So you see, the term y minus a into a square will be real, and so on. Only iz into a square will be imaginary, and iz into b square, this should be b square, it's a typo. So what we do is we compare imaginary parts and we get minus iz, and then we have a square by y minus a square plus z square plus b square by y minus a square plus z square, and so on. Now we take all on left hand side to right hand side, we take ij common, we have 1 plus and so on. Now if we see a is real, y is real, a is real and z is real. So this whole term will be non-zero. And this will be non-zero also. So this entire term inside brackets will be non-zero. But right hand side is 0. Therefore z must be 0. Now z is 0, that means imaginary part is 0 and this whole thing will be real. Problem 64 says that find all the real numbers x such that 1 plus 4i minus 2 to the power minus x less than equal to 5. Now if you observe this carefully, then you will find that 1 minus 2 to the power minus x should be less than 3. Because if it becomes more than 3, then mod of 3 plus 4i will be more than 5. So the limiting value of 1 minus 2 to the power minus x is 3. That means minus 2 to the power x is equal to 4. That means x is equal to minus 2. But when we solve this, you will see some problem. So to solve this, we have to square this. When we square this, an extra root comes into picture, which is minus 3. So we don't have to consider minus 3 for this. Okay. In any case, you will see that how it works out. All right. So we let 2 to the power minus x is equal to p and we solve. We get 1 minus p is to be less than plus minus 3. So p should be greater than 4 or minus 2. So the actual value which we take is when you have to have both greater than 4 and minus 2, then obviously minus 2 will be removed because since it has to be greater than 4, so it cannot be between minus 2 and 4. So if p has to be greater than 4, then x has to be greater than minus 2. And p cannot be less than 0. Okay. So p is minus 2 to infinity. So that a unimodular complex number not purely real can always be expressed as c plus I by c minus I for some real c. So since the number is unimodular, we take mod of z is equal to 1. So z is equal to cos theta plus I sin theta. Now we have to prove that cos theta plus I sin theta is equal to c plus I by c minus I. So we rationalize the right hand side by multiplying and dividing with complex conjugate. So this should be c plus I, not c minus I. It's a typo. So when we do that, we get c square minus 1 plus 2ic by c square plus 1. We compare real and imaginary parts, we get cos theta is equal to c square minus 1 by c square plus 1. So from trigonometry, we know that c will be plus minus cot theta by 2. Similarly, we have sin theta is equal to 2c by c square plus 1. So we know that c will be cot theta by 2 and tan theta by 2. The common value in both, when we compare both, we get cot theta by 2. So the value of c would be cot theta by 2. Problem 66 says that if z cube plus 3 whole square is equal to minus 16, then find mod of z. So minus 16 can be written as 16i square. So z cube will become minus 3 plus minus 4i, because when you take square root, it will become plus minus 4i and then you bring 3 to the right hand side. So mod of z cube will be 5. Therefore, mod of z will be 5 to the power 1 by 3. Problem 67 says that if sin x by 2 plus cos x by 2 minus I tan x by 2i 1 plus 2i sin x by 2 is real, then find the set of possible values of x. So in this case, we again rationalize using the complex conjugate of denominator. So that is 1 minus 2i sin x by 2. So we multiply and divide by both. So we are given that it is real, so imaginary part will be 0. So we look, since it is rationalized, the denominator will be real. Now we look at numerator. So tan x into 1, that will be one part of imaginary, and then 2i sin x by 2 multiplied with sin x by 2 plus cos x by 2, that will be imaginary. So minus tan x minus 2 sin x by 2 cos x by 2, this should be x. Minus 2 sin x by 2 cos x by 2 will be 0. So we take 2 sin x by 2 common from these two, we get sin x by 2 plus cos x by 2 plus tan x can be written as sin x by cos x, which is 2 sin x by 2 cos x by 2 by cos x. So this we take out 2 sin x by 2 common from the entire thing. That should be equal to 0. That is one case. In this case, x is equal to 2 and pi. Now the other thing will be sin x by 2 plus cos x by 2 plus cos x by 2 by cos x. So this can be 0. Now you convert all this into tan x by 2 form, and then you get tan cube x by 2 minus tan x by 2 minus 2 is equal to 0. Now, if alpha is a solution of this equation, then the set of possible values will be 2n pi plus 2 alpha. Problem 68 says that prove that mod of z1 plus z2 square plus mod of z1 minus z2 square is equal to 2 into mod of z1 square plus mod of z2 square. So like the a plus b1 we solved earlier, where we have to prove that a z1 minus b z2 whole square plus mod of that plus a z2 minus b z1 minus a z2 mod of square is equal to a square plus b square into z1 mod of z1 square plus mod of z2 square. That problem we have solved. Similarly, we can substitute that method here. So we let z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2, and we simply substitute this and evaluate to get the desired result. There is a typo in this problem. This should be x plus, this should be plus, because if it is minus, then the root will not match what we need. If x square plus x plus 1 is equal to 0, then find the value of sigma n is equal to 1 to 5 x to the power n plus 1 by x to the power n whole square. So if x square plus x plus 1 is equal to 0, then x will be, okay, it's not a typo actually, it is correct, it is minus. So if x square minus x plus 1 is equal to 0, then x is equal to minus omega square. So we expand the term inside the sigma, and we get x to the power 2n plus 1 by x to the power 2n plus 2. Then we simply combine the powers of x in one term and powers of 1 by x into another term, and 2 when we add will become 10, because there will be 5 terms. So that is another term. We substitute with minus omega and we get these values, and when you simplify this, you will get minus 1 into minus 1 plus 10, which will be 8. Problem 70 says that if 3 to the power 49 into x plus iy is equal to 3 by 2 plus square root of 3 by 2 into I whole to the power 100, then find x and y. So what we do is we take root 3i common from the right hand side. You get 1 minus I root 3 by 2. So we raise power whole to all this. We get I to the power 100, 3 to the power 50 minus omega to the power 100. So if you see this carefully, minus omega to the power 100 would be omega, because minus to the power 100 will be plus, and omega to the power 100 is omega to the power 99 into omega. Now 99 is a multiple of 3, so that will become 1. So this will become omega. I to the power 100 is 1 because it is multiple of 4, and 3 to the power 50 will be left as it is. Now 3 to the power 49 will cancel so many powers of 3 to the power 50, so only 3 will remain. X plus iy will become minus 3 by 2 plus 3 root 3 by 2 into I. Now if you compare real and imaginary parts, you will get x is minus 3 by 2 and y is equal to 3 square root of 3 by 2. So with this, we come to the end of 7th set of problem. I hope that you have found this video useful. If you find this video useful, please subscribe to the channel and like the video so that the video can reach more people like you and benefit them. So it's a bit of help you can give to your batchmates or classmates or other people all over around the world. So I'll see you in the next video with the next set of problems on complex numbers. We are nowhere close to finishing complex number problems, because I estimate that there will be close to about 300 problems on complex numbers. So keep watching, and thanks a lot. Enjoy.